Hi Carmen, how are you doing today?
My day is wonderful. In school today I had English, math, history, and data science. I love data science. It is so fun, but I have so many questions.
Okay, my Carmen. You are so smart and questions are always good. What kind of question did you have today?
Well, my teacher mentioned a few things. First, what is a square matrix?
Okay. Think about a checkerboard that has the same number of squares in each row and each column. That's pretty much what a square matrix is, but instead of squares, we have numbers.
Okay then. What is the trace of a matrix?
For that one, imagine you've got a checkerboard that's just black and white squares. The trace of the checkerboard would be the sum of the numbers if you went from top left to bottom right, only counting the squares in a straight line, the diagonal.
Wow! That is so interesting. So then what is the determinant of a matrix?
My dear, this one is a bit trickier, but let's imagine that our checkerboard is a magic carpet. The determinant is like a magic number that tells us how much space the magic carpet takes up when it's flying. If the determinant is 0, the magic carpet is flat and can't fly.
Very good. I am understanding more now. My teacher also mentioned the properties of trace. What is that?
Okay. Now his involves some rules about what happens when we add or swap the rows or columns of our checkerboard matrix. They are like magic rules that always hold true. One rule says that you can add the traces of two matrices just like you'd add the numbers normally. Another rule says that you can flip the matrix and the trace stays the same.
Then what are the properties of determinant?
Just like trace, determinants also have their own magic rules. One rule says that if you flip the checkerboard, the determinant, our magic carpet space number, stays the same.
Very good. I really like this class. My teacher mentioned an orthogonal matrix. What is that?
My dear, imagine a square that doesn't lean to any side, it's standing perfectly straight. That's an orthogonal matrix. If you tried to flatten this perfect square, made it have 0 space, it wouldn't let you. That's why its determinant, remember, the space number, is always either +1 or -1.
Then how about an invertible matrix?
So think about having a magic decoder ring that can be used to solve a secret code. But there's a trick, the ring only works if a certain number, the determinant, isn't 0. If it is, you can't solve the code.
I got it. So when we are computing trace and determinant, we can use some special tricks to find the trace and determinant of a matrix. We can even use these tricks to simplify the process of figuring out these numbers.
Yes, yes, and yes. You are so smart. You are learning. What other questions did you have?
Well, I am still curious about many things.
We, my dear, ask away. I love when you have questions.
Well, what are these eigenvalues and eigenvectors?
Think about them as special markers and their scores in a game called matrix transformations. Eigenvalues are the scores, and eigenvectors are the markers that get these scores.
How does a marker become an eigenvector?
Good question. A marker becomes an eigenvector when, after playing the matrix transformation game, it may change in size, but it stays pointing in the same direction.
So what's this game, matrix transformations?
Well, it's like a magic box that can stretch, squash, or rotate things you put into it. A matrix is the rulebook for how this box changes things.
Are the eigenvectors and eigenvalues always the same for every game?
Nope, each matrix transformation game has its own set of eigenvectors and eigenvalues.
Can an eigenvector have more than one eigenvalue?
No, in each game, every special marker or eigenvector gets exactly one score or eigenvalue.
So then how many eigenvectors can we have in a game?
Great question. It depends on the size of the rulebook. If it's a 3x3 rulebook, You can find up to 3 special markers or eigenvectors.
What if a marker is already pointing in the direction it should after the game?
That's a brilliant observation, sweetheart. This marker is indeed a special one, an eigenvector, with an eigenvalue of 1 because it stays the same size.
And what happens if a marker doesn't move at all?
Another great question. If a marker doesn't move, it's still an eigenvector, but its eigenvalue or score is 0 because it didn't change in size.
Now I am really curious. Tomorrow in class I will have a blast. So tell me, what did my teacher mean when he said that a matrix is invertible?
Well, if a matrix is invertible, it means you can reverse the changes it makes, kind of like rewinding a YouTube video.
Wow! So, can a matrix transformation game be reversed?
Some can, some can't. The ones that can't be reversed are those with a marker that doesn't move at all or has an eigenvalue of 0.
Why can't we reverse the game if a marker doesn't move?
Because in that case, we've lost some information that we can't get back. It's like erasing a part of a drawing. You can't redraw it exactly as it was.
I am really starting to like this class.
Wonderful. Ask me a few more questions. I am all ears.
What happens when we play with a spinning plate, like an orthogonal matrix?
Oh, that's a fun one. The markers might spin around, but they don't stretch or squash. The tricky part is that sometimes you have to use imaginary numbers for the scores.
Now remind me about those trace and determinant things you mentioned.
They're like special ways of adding up and multiplying the numbers in the rulebook, respectively. They can give you clues about the scores or eigenvalues of a game.
Can we always figure out the eigenvalues using these clues?
For small games, like with a 2x2 rulebook, we can use these clues to find out the scores or eigenvalues. For bigger games, it can get a bit trickier.
I am so happy that you helped me with these subjects.
You are always welcome, my dear. I enjoy helping you with your homework and hearing all of you brilliant questions. Thank you so much for joining us. Remember to like, comment, and subscribe to enjoy data science learning videos. Have a wonder day.